Welcome to College Algebra. In this lecture video, we are going to continue with section 5.2 with our applications of exponential function. So we went through the population growth, we went through the limited growth, and we also went through the radioactive decay type of problems. So in this lecture video, I want to talk to you a little bit about compound interest type of application, and we're going to do some model of cost and the revenue and depreciation type of application problems. Alright, so this is not that bad. Alright, I mentioned the number E last time. It's just a irrational number named by Leonhard Euler back in 1741. The base E, what we use the number for, is just another base, okay, other than our regular other numerical value type of base. Okay, this is 2.71828 something. We will begin to see this base E quite more often. Alright, so as far as a compound interest formula here, okay, it's an exponential explosion on the money. So P referring to the principal, your initial investment, okay. A sub T means the amount after, okay, so many years, compounded so long, that will be the total amount of money that is in your account. So this A sub T has principal plus the interest in it. Alright, your R is your interest rate, T is your time in years, and the lowercase n represent how many times does the account compound in a year. Okay, let's go by in a year. So let's say if we hear the word annually, annually means your n is equal to 1. It compounds once in a year. The account roll over once in a year. What that means is the account will automatically take your principal and plus the interest you earn, okay, and roll into the following year. Okay, your account mature once a year. You roll over, automatically roll over 1 year at a time. Alright, semi-annually. Okay, semi-annually means N is 2. The account roll over twice a year. Alright, quarterly. N is equal to 4. Every 3 months the account will roll over by itself. Take the principal plus the interest, all those money roll into the following compounding period. So that means the P, okay, for the second, okay, go around on the compounding is actually going to be higher than your initial principal, your initial investment, because I'm taking the principal plus the interest from the previous compounding period and roll into the following ones. Okay, so therefore it creates an exponential explosion on the money over time. This stuff is over time. It does not, you don't make a lot of money right away. All right, monthly. That means N is equal to 12. Then we can also have daily, which is 365 or 360. Depends on what the homework will like you to do. Alright. Continuous compounding formula, okay, is referring to when the N gets larger and larger and larger. Okay, if I'm compounding continuously, that means as N approaching to infinity, eventually this part of the formula, okay, can actually be derived into my number e raised into the r times t power. Okay, and the way how the way how you derive when n go into infinity and becomes e to the rt power is actually in the textbook. Okay, so continue. So when we read this problem, you got to know whether the question is asking compound continuously or just a regular compounding problem. All right, so let's take a look. So let's say Chester hoped to earn $1,200 in interest. Okay, we want to earn $1,200 in interest in 2.6 years. Time from $48,000 that he has available to invest. Okay, so if you look at my formula here, I picked this one because I think the problem does say just compound. To decide if it is feasible to do this by investing in an account that a compound annually. See that word, compound annually? He needs to determine the annual interest rate such an account will have to offer him to meet his goal. What would be the annual interest rate have to be? Okay, so basically this problem is asking you to find the interest rate R. Alright, so when the problem says compound annually, that automatically put my n as 1. Okay, this is the problem never say compound continuously, so this is just a regular using the compound interest formula. Alright, time is 2.6 years, goes right here. $48,000 is what he has available. Okay, so that's it. That will be his initial investment. So I got my P, I got my N, I got my T. I'm looking for R, so I need my A sub T. So A of T is the amount of money he will have after, okay, after 2.6 years. So what he wants is earn $1,200 in interest. So in his account, he will have more than $1,200 because he already put initially $48,000 in there. So my A sub T got to be $48,000 plus the interest he wants. Okay, because A sub T means the amount of money in your account after so much time. So what's in it got to be principal plus the interest. So that means at the end he will have $49,200 in his account. Alright, so now this problem becomes $49,200 is equal to initial investment $48,000 times 1 plus R, I don't know, divided by compound annually, n is 1, raised into the 1 times 2.6 years. Alright, if I was simplified, let me push this down. If I would simplify this a little bit, R over 1 is still R. 1 plus R is still 1 plus R. So that's 48,000 times 1 plus R. Raising to the 1 times 2.6 is still going to be 2.6. Equal to 49,200. Alright, so just like with other problems we've done in this section, this whole right hand side is only one term. Right now my R is trapped inside the parenthesis. So a lot of students' first instinct is do a distribution. You cannot do that because this actually has an exponent. okay, on top of the 1 plus r. So slowly peel off, okay, things around my r. The first thing I would do is, since this is only one term on the right side, I will divide both sides by 48,000. Now I'm going to put this in my calculator right now, and what I want to see is clean decimals, okay? If it's not, then I'm not going to write all these crazy decimals. So I'm going to divide by 48,000. Is this clean? This is actually quite clean, because the decimal ends at 5. So I can say 1.025. So if this is real, if this decimal places is kind of long and doesn't seem like to stop, then you might want to just write it this way, okay, rather than actually divide it. Okay, so tell you what, I'm not gonna write this. I'm just gonna still write like this way, so I can type in everything at one time in a minute. I'll show you how to do that. Show you how to do it that way, because most of the students will instantly divide them. So I do want to show you how we can do this without dividing so quickly. All right, so this side will be look like this, equal to. All right, this canceled out, so that will just leave me with 1 plus r to the 2.6 power. So to get rid of the 2.6 power, I'm supposed to take a 2.6 root on both sides. So rather than take a 2.6 root on both sides, okay, I can write them as, let me do it right here. I can write them as 49,200 over 48,000 raising to the 1 over 2.6 power. Okay, rather than taking a 2.6 root, I can rewrite my radical as a fraction exponent. I think we've done that one time with the bacteria problem right here. Okay, same idea. Alright, so that will give me just 1 plus r, because 26 root here will cancel out the exponent. It'll be 1 plus r. So to get r by itself, I will move my positive 1 over. So what I should have is all this minus 1 equal to r. Okay, run 2 decimal places for my r. Okay, so let's be careful here. Okay, let's be very careful what the problem wants. Parentheses 49200 divided by 48,000, close parenthesis, raising to the parentheses. Let the calculator divide this for me, close parenthesis. Then we minus 1 on the outside the parenthesis. Okay, so this is my interest rate. Alright, in terms of a decimal notations, so times 100 to convert into a percent. Then I can run 2 decimal places, so that will be 0.95%. 0.95%. So make sure you times 100 to convert back to a percent. Alright, so that would be the interest rates. Alright, same type of problem. Now this one just compounded differently. So Martha invests $7,800 in the new savings account. So the Martha's initial principal, $7,800. The new savings account, which earns 5.1% annual interest. So the R is 5.1%, compounded monthly. When they say compounded monthly, that means my N will be 12. What will be the value of her investment after 5 years? So T is 5. Alright, so the amount of money after 5 years will just be the principal times 1 plus, all right, interest rate 5.1%, that will be 0.05, right? 0.05 is 5%, just attach a 1 behind it, over 8 compound monthly, n is 12, whole thing raising to n times t power, n is 12, times t is 5 years. Okay, so when I put this whole thing in the calculator, I'm gonna put 12 times 5, which I know is 60, but I do want to show you, if I want to type in 12 times 5, I'm gonna put them in the parentheses. Okay, when I enter it. Alright, 1 plus 0.051 divided by 12, close parenthesis, raising to open parenthesis, n times t. There you go. That will be how much money in my account. Run to the nearest cent. That will be 10,060 and 16 cents. That will be my answer. Alright, let's try an example with compound that continuously. So Ava invests $8,000 in a new savings account which earns 4.8% annual interest, compounded continuously. So when you hear the word continuously, okay, we will use this formula here on the right. What would the value of her investment after 7 years? So what that means is compound continuously means this n just gets larger and larger and larger and larger and larger. That means n is approaching to infinity. Okay, that eventually lead to this formula. Alright, so that will be initial investment $8,000 times base E to the R, 4.8% is 0.048 times t is 7 years. Time gotta be in years. Alright, I'm gonna put that in the parenthesis, okay? Because I want the calculator to multiply first before base E raising to that power. So 8,000 times second e to the x. Okay, that gave me a parenthesis 0.048 times 7. So round to the nearest cent. So that will be 11,194 and 71 cents. Okay. Very good type of problem regarding to how an investment. You know, talk a little bit about investing money into like mutual fund and things like that, or certain type of savings account that actually have a high interest. Okay, and the way how to calculate how much money you will have, probably using some sort of compound interest formula. Alright, another set of problem I want to show y'all is the cost models, and also involving with revenue and depreciation. So this function c sub t, okay, models the rise in the cost of a product that has a cost of c today. Okay, capital letter C is the value today, the cost of today. Alright, subject to an average yearly inflation rate. Okay, so this problem is about inflation. Inflation occurs annually. So the R is inflation rate for T number of years. If the average annual rate of inflation over the next 15 years is assumed to be 1.5%. Okay, so let's assume average annual inflation is 1.5%. What would the inflation adjusted cost of a $27,300 motorcycle be in 15 years? So this is basically talking about cost of living is increasing over time because of inflation. So we can actually predict, okay, how much things cost in the future. Okay, so today's cost for this motorcycle is $27,000, but if we go with the inflation and for the next 15 years at 1.5%, that same motorcycle 15 years later, okay, should actually cost higher, okay, due to the inflation. All right, let's check it out. Okay, C of T. T is now 15 years. Excuse me. C of 15 years. Set it equal to the cost today. 27,300 times 1 plus. All right, my inflation rate 1.5% is 0.01. 0.01 is 1%. 1.5% would be 0.015 raised into the 15 power. So this is a lot like the compound interest formula, except my n is 1. Okay, because it's annually. The inflation rate calculated annually. That's why I didn't write over 1, that kind of stuff. That's why we don't see this over 1 thing. So this is practically a compound interest formula. 1 plus 0.015 raising to the 15 power. So the same bike today is $27,000. 15 years from now, $34,000. Okay, 131.34 cents. All right, so that's about inflation. Now this problem is really interesting. The revenue function. Okay, make sure you understand this. The revenue function look like this. Okay, where X, this X represents the number of units sold, and P of X is the unit price. All right, if P of X, the unit price, is equal to this function, find the revenue. Okay, let's just find the revenue if 20 units are sold. So 20 units go, it represents X, because X is the number of units sold. So be very careful here. Okay, my revenue function is the number of units sold, which is X, which this problem want me to do 20, times my P of X. P of X representing the unit price. Right now my unit price is this function, so that means this function will go to where that piece of X is. So that'll be 20 times 26 times 4 to the negative X over 4. So that'll be negative X is 20 over 4. Okay. So what's my revenue for selling 20 units? So it'll be 20 times 26 times 4 raising to the negative 20 over 4 is negative 5. There you go. Round to nearest, round to 2 decimal places, so that's about 51 cents. Okay. We're about to write $51. 51 cents, that'll be $0.51. Okay, so that's the revenue. So most of the time, when we selling stuff, we know how much we sell, and we know what is the price for 1 unit. Okay, that I set. The unit price is set. Okay, by just based on based on how much more you want to sell for. You know, if you bought something for $10, you want to turn around selling it, you might want to charge $20. Okay. So just like those Krispy Kreme donuts tickets, you can buy a stack of those tickets for fundraiser. Okay, that is costing you X amount of dollars. So when you sell it individual donut tickets, okay, you raise the price a little bit higher. You know, maybe $7, $8 is what people are selling for around here for those, you know, fundraiser donut tickets. But for more sophisticated companies, they actually have a way to figure out what their unit price need to be. Okay, and unit price, you know, you gotta think about things like the cost of materials, you know, transportation, all that stuff. So when Walmart, you know, when all the goods selling on the Walmart and the department, you know, all those big grocery stores, you know, anything that these big store sells, those unit prices set based off certain things. Okay, there are different factors how much they want to charge. Okay, the shelving also costs money for the companies. Okay, so for bigger companies, the unit price can be more sophisticated. Just like what you see here is a type of function. Okay, this number is set. You know, these numbers are determined by certain factors. Okay, so that's the reason why, you know, geez, Mr. Chen, so 20 thing, you only revenue 51 cents. Okay, that's not really a lot. So, because those big stores, you know, they want to, you know, they're selling by, you know, tons of quantity. Maybe they're selling 20,000 units. So imagine I put 20,000 there. People just add a couple more zeros. That's 200. That's 2,000. That's 20,000 units. So that's making what, $500 revenue. Okay. All right. Let's try another type of problem here. The concentration. Interesting. Of a certain drug. So C sub T representing the concentration of a certain drug in the bloodstream after T minutes is given by the formula like this. Okay, I'm using a base E here. What is the concentration after 8 minutes? So basically, concentration in the bloodstream actually decrease over time. That's why if you actually look at this part right here and think back, my population model, E to the KT power, when that number K in front of the T is negative, that means what? Decay or depreciate or go downward. The Y value go downward. So the problem makes sense. You know, when we take when we take any type of drugs after so long, okay, the concentration actually decreases. So let's see what happens after 8 minutes. So 0.04 times 1 minus E to the negative 0.2 times 8 minutes. Alright. So the problem doesn't offer any type of units. So I have no idea what these what this 0.4 represents. Just some type of concentration. How many, how much amount of, medicine or drug still in the bloodstream. 0.04 times 1 minus second e to the x. Okay, in that exponent, I'm going to type in negative 0.2 times 8. I'm going to close the parenthesis for that exponent, close parenthesis for my 1 minus. Okay. Going to 3 decimal place, that will be 0.032. Okay. So if I will increase my time, so the whole idea here is increasing the time, maybe like 60 minutes. Maybe 60 minutes later, how much concentration is left in the body? Okay. 0.04. That's weird, ain't it? After 60 minutes, the concentration of a certain drug in the bloodstream is actually went back up almost to what we had. That is very strange. Why? So maybe what the problem is trying to say is when we first took the drugs, the concentration in the bloodstream is actually lower because, see, this number is very strange. The negative sign is supposed to, the negative sign in front of the 0.2 is supposed to tell you the concentration decrease. But since my E is normally 2.7 something, but the minus actually make my Y value, the Y value is supposed to go downward, like I showed you back in 5.1. Okay, it's an exponential. The Y value decreases from left to the right, but with the negative sign in front of it, the Y value go backwards again. So what this problem I'm trying to say is, when you take the medicine, medicine's in your belly, but slowly it actually release into the bloodstream. Okay, so as the time goes on, more amount of the medicine actually went into the bloodstream. That's the reason why when I increase, just for the curiosity, increase the time, I almost get 0.04. Okay, which is what my initial amount started with. Okay, interesting problem. Alrighty, so that will conclude our application of exponential functions. We will do another set of application problems at the end of lecture video 5.5. Thank you for watching.